Merhabalar herkese, tüm dinleyicilerimize ve değerli konuğumuza hoş geldiniz diyorum. Bugün kısaca ai olarak söylediğimiz İstanbul Teknik Üniversitesi Yapay Zeka ve Veri Bilimi Uygulama Araştırma Merkezimizin ikinci seminer serisine başlıyoruz. Kendimi tanıtayım ben öncelikle. Şule Gündüz Öğüdücü. Bilgisayar ve Bilişim Fakültesi'nde geçen yıl kurulan Yapay Zeka ve Veri Mühendisliği bölümünün bölüm başkanlığı görevini yürütüyorum. Aynı zamanda İTÜ'nin de merkez müdür yardımcısıyım. Biraz önce söylediğimiz gibi bugün ikinci seminer serimize başlıyoruz. Geçen yıl yine bu zamanlarda çok değerli konuklarımızla ilk seminer serimize başlamıştık. Bugün de yine çok uzaktan çok değerli bir konuğumuz var. Benim için de çok anlamlı. Profesör Doktor Tamer Özsu, Kanada University of Waterloo Bilgisayar Bilimlerinde öğretim üyesi. Hocam hoş geldiniz diyorum. Size çok teşekkürler davetimizi kabul ettiğiniz için. Benim de Tamer Hoca doktoram sırasında danışmanım olarak beraber çalışma onuruna eriştiğim bir hocam. Çoğunlukla dağıtık veri tabanları, geleneksel olmayan verinin saklanması konularında çalışmaları var. Ve bugün de bize veri biliminin tanımı, kapsamı için sistematik bir bakış açısının anlatılacağı bir konuşma yapacak. Tabii ki veri biliminin tanımı için çok fazla materyal bulmak mümkün. Ama bunu sizin tecrübelerinizle, sizin bakış açınızla, sistematik bir bakış açısıyla, sizin perspektifinizden dinlemek bizim için çok ilgi çekici. Ben de merakla, ilgiyle bekliyorum bu konuşmayı. Dinleyicilerimizin soruları olursa söyleşi sırasında YouTube chat ekranını kullanarak sorularını yöneltebilirler. Söyleşi sonunda vaktimizin yettiği ölçüde bu soruları hocamıza iletiyor olacağız. Hocam sözü ben size bırakacağım. Öncelikle belki kısaca kendinizi tanıtırsınız konuşmaya geçmeden önce. Sizi dinliyoruz hocam. Çok teşekkürler tekrar katılımınız için.
Çok teşekkürler Şule davetin içinde. Bu konuşmayı yapmaktan ben de çok mutluyum. Kendimi tanıtmak için fazlaca bir şey yok. 74 ODTÜ Endüstri Mühendisliği, 78 Master. Sonra Ohio State'de 83 doktora, 84'ten beri de Kanada'da önce University of Alberta, sonra da University of Waterloo'dayım. 35 seneyi aşkın süredir akademisyenlikle uğraşıyorum. Şey yaparken Şule'yle bu konuşma hakkında görüşürken benim slaytların hepsinin İngilizce olduğu konusunda bir kuşkumu belirtmiştim. Şule de konuşmayı İngilizce yapabileceğimi söylemişti. Onun için bu noktadan sonra İngilizce döneceğim. Umarım kusura bakmazsınız çünkü slaytlar Türkçe değil.
Evet hocam ben atladım söylemeyi. Konuşmamız İngilizce, yani konuşma İngilizce olarak devam edecek. Ama sorular İngilizce'de olabilir, Türkçe'de olabilir. Daha sonra yani soruları karışık alabiliriz diye düşünüyorum.
Tabii.
Duygusun tamam.
Ben şeyi yapayım, slaytlarımı edeyim, başlayayım o zaman. My slides. Why are my slides not showing? Okay. Share. Okay. Okay, thank you again for the invitation. I'm very happy to be here, even if virtually. Hopefully, fairly soon we will be able to do this in person, but we still have some time to do that. Most of my talks are deeply technical, but this one will not be very technical. I want to talk about how I think about data science and how we can systematically look at data science. This is a topic I've been thinking about for a number of years because I've been working on some initiatives that force me to think what data science is and how it should be organized. The question is really important in its own right for two reasons at least. One is that the topic is becoming important and there is a lot of confusion on what it really is, how it differs from some of the other areas. The second is that there are lots of research institutes, centers, and even academic units being formed around data science. And many of these do not have a fairly well-defined vision of what they mean by data science. So they usually fit in within the constraints of their institutional internal politics. That's unavoidable, but it still is important that there is a particular vision and from which the mission of these centers and institutes come out. There is another important issue, which is that there is an ongoing discussion as to whether data science is an academic discipline. And I'll say a few more words at the end on that issue. But if it is going to be an academic discipline, then we really need to be able to define it far more precisely than we're able to do right now. So my objective in this talk is that I will give you how I think about it, what I think data science is, and how I think it should be organized. And maybe we'll have a discussion at the end of it. All right, so let me do, okay. So the data as a major asset of organization is now well recognized. It is recognized that it is perhaps the most important asset of organizations. This has become widespread to the extent that it gave rise to what is we now call big data revolution. And big data revolution then got moved into data science, and it's now recognized as one of the most important IT developments of the last few years. The discussions about big data and data science and so on are all over the news. I'm sure we've all read a lot of them. And now the cartoons have started around data science and big data. And when you're the subject of Dilbert cartoons, then you know that this is now catching on and it has become commonplace. However, there is significant confusion around the term data science and what it means. This word cloud was generated a few years ago from publications and around this topic, and it demonstrates what the confusion that prevails in the wider community on the topic. So therefore, data science really needs positioning. And what I want to do is to help with that positioning. So the talk is divided into 5 parts. The first part, I'm going to talk a little bit about how I view data science, starting with some basic definitions. Then I want to move into some data science applications, and I want to do that first because for me, data science is really grounded in applications. If you don't have applications, you really don't have data science. Then I'll talk about the ecosystem, how I view this entire data science ecosystem, followed by a discussion on the life cycle. What is the development life cycle? And what are some of the architectural issues there? And finally, I'll hit on the touchy subject of who owns data science. So let's start with looking at some definitions that you can find in literature and elsewhere. Of course, we first go to Wikipedia, and that's where we always go, it seems these days, when we're looking for a subject. And Wikipedia definition captures a number of important aspects of data science. It's data-driven science. It talks about knowledge extraction. It talks about gaining insight from data. And all of these are components of data science, and they are important. But then it goes on at the very end, and it says it's similar to data mining. I will argue in this talk that while data mining has an important role to play, it really is not the equivalent to data science. So we shouldn't be assuming that there is an equivalence there. And the earliest mention of data science I could find is in this paper. And the definition that it gives is really captures a lot of it. It's a bit wordy, but it captures a lot of it. And if you look at the footnote of this is from 1998. If you look at the footnote, it refers to a meeting where this topic was discussed. So it appears that the introduction of the word data science predates that paper. Many of us in computer systems and databases would know about Jim Gray and his work with astronomers in the Sloan Digital Sky Survey. This is the Sloan Digital Sky Survey is perhaps one of the earliest successful demonstrations of the power of data-driven science. And the fourth paradigm is a book that was published in 2009 and collects a number of essays that touch upon this subject. And this comment that I've quoted is from the preface of the book, which says that the data science or data-intensive approach is a new paradigm, and that certainly is true. And let me point out to this small book. It's not a big book, which defines data science in a fairly nice way. But then it goes on and says it's these terms, machine learning, data mining, and data science are used interchangeably. That certainly is true in public, but for us, we need to be a bit more precise. Then it says it borrows from these fields, but it's broader in scope, but it never really defines what the breadth is. I worked with a definition that tries to capture the fundamental aspect of data science. For me, it is the data-driven approach to problem solving. So you base everything on data and what you can learn from data. And it involves the process of collecting, managing, analyzing, explaining, and visualizing both the data and the results of your analysis of the data. So admittedly, the second part of this definition is a bit more process-oriented, but I think it serves our purposes. The other aspect of data science is that it is a unifier. It connects many disciplines that are usually thought as disconnected or hard to connect. And as you will notice, many of these disciplines are not STEM. They are not technical, but they're non-STEM fields. And there are a number of those. One can look at this diagram either from outside in or inside out. If you're looking outside in, you basically see that all of these areas contribute and influence what we mean by data science. If we look inside out, then data science is visualized as having an influence and in connecting all of these fields. Let me start with dispelling two myths, but before that, there is this question of who's a data scientist, and I'll answer that question at the very end. Let me start with two myths that are quite common. One is that data science is the same thing as big data. This is true in popular culture, but for us, we need to be more precise. They're not the same thing. Somebody described big data as the raw material, a raw material that has a lot of potential, but now you have to do something with it. And doing something with it or processing it is what allows you to leverage this resource. And that's what gives you the insight. And in important issue, and you've heard me say this before, and you'll hear me say it again, applications are really important in data science. If we don't have applications, we don't have data science. Then we have big data platform, but we don't have data science. So that's one myth that we should, that I would like to argue against. The second is far more prevalent, perhaps, and that is that data science is really machine learning or a subset of it, and machine learning is a proper subset of AI. There are some people who claim that modern AI is all machine learning, but that's a different discussion. To me, this is also fundamentally wrong. There is no question that data science and AI have an intersection in the area of using machine learning, data mining techniques, and in the data analysis component of data science. But data science has many other considerations, and artificial intelligence has many other considerations. So they're not the same. And I hope that I will be able to convince you that they're not the same thing. One does not subsume the other by the end of this talk. So with that introduction, let me talk about a few applications of data science. I have many applications that we can talk about, and I'll come back to this issue that the applications are king, but I'm not going to have time to go through all of these applications. I'll give you a few examples, and in the fuller version of this talk, I have far more applications, but our time is limited. So one common application that I'm sure we're all dealing with is fraud and fraud detection. Fraud detection application is heavily dependent on data and data science. You look at past transactional data and predict or determine whether the particular transaction you're looking at now is fraudulent or not. The data in this case is streaming data, and I'll talk about that more. All of these transactions are streaming into the system, and you're making a decision more or less in real time, but the real time is not instantaneous. There is a lag there. There are elements of real-time decision-making with some relaxation. What complicates the problem here is that precision is important. It's not only coverage that's important, but precision is important. Both false negatives and false positives are problematic. You don't want to miss fraud, which means that you really want to be complete, but you don't want to be imprecise either. So this is a typical data science application. Another typical data science application is recommender systems, where you're making offers or recommendations to users based on their past activity. This is really important in commerce. Netflix, for example, indicates that their recommender system is valued at $1 billion per year. Amazon says that their recommender system drives 20 to 35% lift in their sales. So these are important, and similar to fraud detection, recommender systems might also use streaming data and processing. So this is another important application. One application that's really dear to my heart these days, and I'm looking into this quite a bit, is sustainability. And sustainability is touching multiple things: food, energy, water, and this entire issue is multidisciplinary. The environmental problems that we're facing has reached crisis point, and we need to tackle it in a multidisciplinary way, and data science is one way of doing it. This is an area which is very rich in data. There are lots of data from Earth observation data, satellite-based systems, ground-based observational data, citizen scientists produced data, and so on, and leveraging all of that data for analysis and then decision making is important. I will end my example applications with this example from sports. You might have seen this movie. If you haven't, maybe you want to. It is kind of a fun movie, but it's real life. The movie explains this baseball club in US, which really focuses on Oakland A's, which had a very low budget, and they were not able to compete. So they moved from usual way of recruiting players and forming teams to using statistical analysis of baseball data to find gems in sand, with really finding players who are potentially going to make the team stronger, but nobody is looking at those players because the traditional way of or the metrics that they use is not there. And they had when they used data science-based techniques in 2002, they had a very, very nice record, joint second in the league, but they had a total team salary of 40 million, while the other joint winner in the league had 120 million. So this is really another example of how data science has helped in the domain of sports and sports management. All right. So one take-home message from the talk today is that applications are truly important, and we're trying to define what the data science problem is in these applications, and we wish to solve it by making data-based decisions. So let me talk about the data science ecosystem. How should we think about data science? For me, data science ecosystem consists of 4 foundational building blocks, or what I call pillars: data engineering, data analytics, data security and privacy, and data ethics. You will notice that data analytics is one of these, and this is where data science and AI and machine learning intersect. But there is a whole lot more to the data science ecosystem that beyond this data analytics portion. So this is the second. This slide is the second take-home message that I'm hoping you will take from the talk, namely that data science is interdisciplinary, it is broad in scope, and it has a number of non-STEM components. Data ethics, etc., are not STEM topics, and even a lot of data security and privacy are policy-based, and they're not STEM. So in the next little while, I'm going to dig into each of these 4 pillars. You can guess that my objective is not to do a full survey. We don't have time for it, and this is not the talk for it. But I want to highlight what the issues are in each of these areas and why I think they're fundamental pillars of a data science ecosystem. So data engineering is really all about the big data management. How do we how do we manage this big data? I haven't defined big data, and I'll come to it in a second, but keep in mind those 4 V's. But that is really the big issue in data engineering. What do we do with data? With the data, And within this broad context, data engineering worries about data processing platforms, typically the software platforms for processing data, integrate how we do data integration, because we do data science uses data from many different sources. They need to be integrated, and the data lake concept is prevalent these days. Because we're using data from many different sources, data quality issues arise when we integrate. What are those? Now, how can we address these issues? And finally, the data needs to be trustable. So because we're using various sources, the provenance of the data, who generated the data, where it comes from, becomes important. You might wonder why I worry about this. Why data engineering is a big pillar of data science, in my view. Well, the answer is fairly simple. If you do not manage your data properly and get it into a shape that's trustable and clean, it really won't matter how great a model of your data you generate. The results are going to be junk. So this garbage in, garbage out really applies here. And the purpose of data engineering is to make sure that you do not put garbage in. Let me give you an example. You might have seen this news from October of last year, where the news was about the UK public health system, where they had a problem with all of the data that they were collecting about COVID patients and tests and so on. As it turns out, they were using Excel to manage their data, and they were using Excel in the old format, XLS format, using templates. And each of those templates can hold about 65,000 lines, Excel lines. And they used 1 line per test. So each template could actually hold about 1,400 cases. So what happened is when they reached the maximum file size, Excel couldn't hold it. And all of that, they just dropped it. And the result was that they lost a huge chunk of their data, or significant portion of their data. So the message is data engineering is important, and don't manage your data in Excel. So what is big data? The 4V, nobody really can define big data properly, but we talk about the 4 Vs. One is the volume, but this is obvious. Big data is big. We're talking about petabytes and zettabytes of data. Zettabyte now is 10 to the 21, so it's really big. But just to give you, there are lots of important issues, but just to give you one example, Alibaba, which is an e-commerce system, or it's e-commerce site in China, reported in a 6-hour period in their very peak, one of their very peak purchasing days. In a 6-hour period, they generated 320 petabytes of transaction log in 6 hours. So that's really big. And more importantly, it's not only the volume is big, but it's growing very fast. This is the quote from Eric Schmidt, and you can actually look at this infographics to see it as well. The growth of the speed and the growth of the data has increased quite a bit. On the right-hand side, there are the different types of data, and that is important for our discussion as well, because they point to the second aspect of big data, which is variety. Data is now generated in very different formats, and most of our expertise in data management is on managing structured data, but all of this other data is unstructured. And the argument is that about 90% of the data that we're generating is unstructured data. And we really need to be able to process this, and that's not easy. because the data it doesn't lend itself as easily as structured data for management and processing. The third is velocity, and this is really what streaming data is. And if the volume is dealing with data at rest, velocity aspect is dealing with data in motion. Data is coming at us at high speed, and you never see the end of the data, and you have to process it. The volume of or the amount of streaming data is increasing. This is the market just for video streaming, and it really is a small portion of it. When IoT comes online and we have a wide IoT deployment with sensors and so on, the amount of streaming data will become serious and will be difficult. And the final V is veracity. This is the uncertainty and incorrectness in data, because we're getting it from very different sources, and data quality. So the big data problem is being able to manage this, and data engineering problem is really taking all of this data and dealing with the issues. So what are the issues? The first one is this integration. All of this data of different modalities from very different sources need to be integrated and integrated in a way from which we can pull out data and do analysis, or use it for access, search or query. And the term data lake is now quite popular for this. And data lakes are the modern forms of data warehouses. The difference is that in data warehouses, the data that you hold in the integrated data is well structured. You do processing as you put into the data warehouse, so the data warehouse has good properties. In data lake, you're much more flexible. You just put in the data, but what you do is you do processing on the way out. Data warehouses are typically called schema and write. So when you're writing into the data warehouse, you make sure that it obeys the schema. Data lakes are typically schema and read. You do a lot of the processing, ETL extraction and proper data cleaning on the way out. Data quality is a huge concern. It is considered one of the major critical factors in the success of data science. And it takes perhaps the most amount of time in organizations in their data science projects. Unfortunately, we don't always treat the data lake and data quality issues properly, and we always lag behind. The aspects of data quality are typically characterized along 6 points: accuracy, completeness, consistency, timeliness, validity, and uniqueness. And I think these terms are self-descriptive, so I'm not going to go into them, but they together make data quality. And the problems, data quality problems that we need to worry about in data science come in 2 categories. One is data unification, which is really what you have to do as you're putting data, integrate into data. The second is data repair. If you notice, how do you detect problems in the integrated data, and how do you repair those problems? And those are the 2 broad areas of what you have to do. So that's the data engineering, first pillar. The second pillar is data analytics, which is what most people think about when they think about data science. And the data analytics is where you apply statistical and machine learning techniques to draw insights from the data. But now you've actually gotten the junk out, so you're not putting garbage in. With the cleaner data, now you can do the analysis. This involves both statisticians and computer scientists, And there's always a discussion as to what their respective roles are. I'm not going to go into that discussion, but this paper I found, which is a short paper written by biologists, I found this paper to be quite revealing. They talk about statistics, drawing population inferences from a sample, and machine learning finding generalizable predictive patterns. So they say statistical analysis creates models, probability models that fit the data, and the model it fills in the unknown, unobserved parts of the system, and it works well with a few dozen variables and with data that typically is considered small to medium size in today's standard. Machine learning, on the other hand, really does prediction by using learning algorithms, and it can handle very large number of variables and very large number of associations between these variables. It's not a differentiation that probably is very important, that the lines between these are starting to blur. The type of data analysis we do in data science comes in four categories. Descriptive, which is what does the data reveal? What does the data tell us? One important aspect of descriptive analysis is exploratory analysis, which either you explore the data and it reveals things that either confirm your hypothesis or reveal things that you never expected. So you really, this is new insight. The second one is diagnostic. Now, if you've detected, if the data is telling you something, diagnostic analysis tells you why this is happening in the data. Why does the data suggest this is happening? Descriptive and diagnostic data are what are retrospective. They look backwards. Predictive and prescriptive, they look forwards. Predictive says, now that I've seen the data looks this way. What can I predict for the future? So if you consider this model as a set of variables, then what are the expected values of these variables? And machine learning fits in this predictive analysis. And prescriptive goes one step further and says, not only am I going to predict, but I'm going to suggest certain courses of action that you should be taking based on this. And this is a fairly popular diagram on the right, which that you will see. And it simply points out that from descriptive to prescriptive, the analysis grows both in complexity and in value to the organization. One of the important issues in data science is that you want to pick the right task, data analysis task, that fits the particular problem you're trying to solve, or the problem that you formulated. And the tasks typically fall into four groups. Clustering, you have a large amount of data and you're trying to group them into clusters. Outlier detection, where you're really trying to find the anomalies in the data that don't fit the rest of the data. Association rule mining, where you're trying to find relationships between variables. The most common application here is market basket analysis. And prediction, where you're trying to predict what will happen in the future. It could be a classification task where you have a certain well-defined number of classes, and you see one item, and you're predicting which class this item belongs to, or a regression where you fit a model to the underlying data, and you're trying to predict what the future value is going to be. And it's really important to be able to do this properly. So that's the second pillar, and that's how data analysis fits in data science. The third is security and privacy, and I'm not sure that I really need to say too much about this because we're talking about large volumes of data that come from many sources. I think it's obvious why the security and privacy is an important concern. But let me open this up a little bit. First, let's look at the threats. Typically, we talk about 4 types of threats in data science, all focused on the actors that are playing in the data science. One is data breaches. All of us probably at one time or another have been subject to one or more data breaches, usually more than one. We get a notice that there was a data leak and our personal data has been breached. That's one. Second threat is surveillance. Both state actors and companies are very actively trying to collect every piece of information for surveillance or commercial gain. That's a threat. Third is misinformation and disinformation. This has become really popularized and very common. People intentionally spreading rumors and mis and disinformation. And finally, the infrastructure attacks, infrastructure both in hardware and software that are under attack. So in data science, these are the 4 big threats, and we need security and privacy technologies to withstand these attacks. And typically, privacy and security go hand in hand. Privacy is concerned with proper handling, processing, storage, and usage of personal information. So it's all about personal information and consent about the use of personal information. Security is focused on protecting personal data from unauthorized access and malicious attack. And these two together form data protection, provide data protection. And the challenges here are fourfold. One is that you have the human in the loop. Many data science projects involve humans, and controlling the information that humans hold is very different than controlling information that are held in computer systems. There are unintended side effects. Even though you've done all of the data engineering and you've fed it into the analysis, and the analysis is careful, there are traces of this raw data that you might find later on in the data science process. And what that will allow you to do is you might be able to link that raw data from multiple sources to reveal information that you don't want to reveal. The third is that the application requirements in data science application requirements are quite different than others. You do a lot of aggregation of the data and so on. And the aggregations, when you do this, have different security and privacy requirements in order for them not to reveal the raw data. And finally, inherent limitations. We have 3 goals. The goals that we have is that we want privacy of the data, but we want utility. This trade-off between privacy level and utility level is well known. But we also want to do all of the security and privacy very, very fast, because the users typically don't want to wait forever for the overhead of security and privacy. And it is not really possible to accommodate all 3 of our objectives. Something has to give, and what gives and what that means for the results is challenging. And the concepts of security in the traditional sense and in data privacy, in data science, change. In the traditional security privacy, it's all about confidentiality. How do we hide the data and the integrity of the data? While in data science, because the data comes from many different sources with many different owners, it is the privacy, the ownership of the data, and the veracity. How trustable is this data? So that's the third. And the fourth pillar is data ethics. Data ethics is not well defined, but it needs to be well defined. It certainly has a strong connection to data privacy and issues, but it's broader. The definition that I found, which I really by more of a philosophical definition, is defines the data ethics as having three dimensions: related to data, related to algorithms, and related to practices. And these three dimensions give you a design space for thinking about ethics, and whatever point you pick in this design space means that you've made certain ethical decisions. The ethics of data have four different perspectives. One is the ownership. Who has the ownership of the data? Who owns the data? And this ownership of data takes different forms in different societies. It's different in North America than it's in Europe, and there are even differences among countries. So that's one concern. The other one is transparency. If you're collecting data about me, I need to know that you're collecting data about me. I need to know how you're collecting it, how you're storing it, and how you're going to be processing it. You might have actually heard of the recent big fight between Apple and some of the others like Facebook and so on, where Apple now on their mobile platform asks you if you want any of these applications to track you and collect data about you, and you can say no. And companies like Facebook and so on are not at all pleased with this because they are used to collecting data without asking your permission. The third concern is privacy. Personally identifiable information should not be revealed in any form. And the fourth is intention. What are you going to do with my data? If you're collecting my data, what are you planning to do? And in particular, secondary uses. You're collecting data, and I've given you consent to collect data and use it for one purpose, the fact that you're not going to use it for something else. Let me talk a little bit about algorithmic complexity and ethics in algorithms, which reveals itself as algorithmic bias, which is very much discussed. This is a very, very simplified workflow of a machine learning analysis when you're using machine learning for analysis. So you collect training data sets, and then you decide which features you're going to include in your model. Those capture your training phase, and then you use this model on actual data sets, and you come to certain outcomes and conclusions. And the important issue is algorithmic bias can enter into the picture in all three of these phases. In the training data set, you can have historical and representational bias. Because you're looking at historical data, certain things might appear much more there. A typical example in North American context is that there are, if you're using police arrest data, certain marginalized communities are going to appear far more in that data because they're over-policed, and therefore the historical data is going to introduce bias into your training set. Representational bias is also the same. In the data set that you collect, there may not be enough female data, and that basically means that your data set is going to be male biased, and that's going to influence your analysis. When you include or you omit certain features, that becomes an issue. If you do not include, there are some things that are called protected variables: gender, sex, religion, etc., etc. So just because you do not include, for example, race in your model as a feature, does not mean your model or the entire analysis is not racist. It might be, you might be ignoring race and therefore introducing bias. And finally, in the outcomes and conclusions, bias comes in the form that we might be having, we might be looking for outcomes, or we might be posing questions that we cannot really measure. For example, we're doing an analysis, and what we're trying to determine is whether a given student is likely to succeed in the PhD program. Well, there is really not much that we can measure about it until the student is either successful or unsuccessful, but is done. So what do? We use proxies for it. And one proxy that is very much used in the admission process are GRE exam scores. Well, GRE exam scores are really very bad predictors of success in PhD programs, and they are culturally biased. So by using these proxies, you're introducing biases into the system. There are lots of examples of this algorithmic bias. I'm going to flash through these. I don't have time to go through it. There are studies that actually show that these computerized models have generated results which say that the Black patients are not assigned high enough priority or risk level in being ill to warrant higher levels of patient care. Another example is what is used in the criminal justice systems in U.S. So these two, the story is that these two were caught for petty theft, small theft, and the female Black was ranked by the system to be a very high risk, and the other person, a white male, was rated as a very low risk, although he had prior arrests. And they looked at what happened in 2 years after this evaluation was done. She had no other arrest, nothing on her record, and he was in jail for repeated violations. So the algorithms are really bad, and these percolate everywhere. And this algorithmic bias comes in. This is not an example, but just a statement that they've done studies about the female participation, how often women are involved in building these models, and the numbers are very, very low. I think in Google, only 10% of their AI groups, the ones who are doing these modeling, are women. At Facebook, it was 15%. They looked at all the authors in 2017 machine learning and analysis conferences, and only 12% were women. So if you're not at the table, the models get designed in a way that introduces bias by omission. I'm going to skip these. The final point about the ecosystem that I want to say is that we give the impression that there are these silos, but the silos are really problematic. Each of us do our work in one corner, in siloed, but the most interesting problems occur at the intersections. So when data analytics and ethics combine, that's where interesting problems occur, where data engineering and data analytics intersect. That's where interesting problems occur. And there are lots of interesting problems in those intersections. And we really need to look at this in a holistic fashion. And data engineering, data science projects need to be multidisciplinary team efforts. So that's that. Let me quickly look at the data science lifecycle. What are we talking about? So in conducting a data science project, I view it as a set of steps from data acquisition leading to data preparation, which is everything that you get the data to make data trustable. And then you integrate the data and you have to manage it. You have to model and analyze it. And then you have to explain it. That's really the important part where we're failing these right now. We're not very good in explaining why the models are producing the results that they're producing. And we have to disseminate it in as widely as possible, perhaps using open data principles. So, and hopefully these will lead to improved decisions and problem solutions. This is a pipeline, and this is a life cycle. Some call it a process, which is fine, but I look at it as a life cycle. And there are these concerns, which is security and privacy and ethics, policy and social impact, that cut across all of these steps in this life cycle, and those are important. They impact every one of these steps, and all of these form the core of data science, but you really need to have these applications to get anywhere. And again, the issue here is each of these steps have their own issues that they need to address, but the issues at the intersections and where they touch each other are equally important, and they need to be studied. One problem with that depiction is that it's linear. It gives the impression that you start from one, you follow those lines, and you get to the other. And of course, that's not correct. And for data mining, a common model for deployment is this CRISP model that has been developed, which starts from business understanding, follows a number of steps with sufficient feedback loops to go back and redo certain things, centered on data. And the outer circle suggests that you keep repeating this. And of course, we can take the life cycle diagram that I showed you and more or less do the same thing in this type of fashion, in a circular fashion for data science. And we have this monitoring phase when you come back and you refine the problem definition. And this would suit us fine. We can look at it in this fashion. It is important. The one thing that I don't like in these circular diagrams is that when you come back to revisit your problem and you refine your problem, it gives the appearance that you're back to square one, but you're never back to square one. You have a much better understanding. So in a philosophical sense, there's a dialectic process going on here, and you're improving what you learn. So that's kind of the life cycle. Briefly on the architecture, there are different ways that one can think about the architecture. I won't have time to go through this, but there are things that are called reference architectures. And a reference architecture is kind of a meta-architecture that defines a family of similar things. So you're looking at what are the functions, what are the similar systems, how can we standardize the nomenclature, how can we define the key elements, and so on. Software engineers have done these studies, so this is one that I'll refer and but won't spend time on. And another one has been defined. But what I'm going to do is talk about a concrete structure, which is really what we should call a software stack. So by definition, this environment is going to be a scale-out. So you need a distributed data store to manage it. You have data processing framework, which is how do you process this data, which is MapReduce type stuff. You might have an SQL interface or scripting interface for access. Since you have multimodal data, you typically need a NoSQL solution. You need a search capability, perhaps streaming processing. And since these are distributed systems, you need resource management to manage the distributed system. And you have data analysis tools on the top. And each of these is a very busy there are lots of systems all around us. So this is more of a computer scientist view of the architecture of data science software architecture. So who owns data science? Let me touch upon that to finish, and I'll take 2-3 minutes. So I talked about the computer science. Within computer science, the argument is that it's all AI, And since I've talked about that before, I'm not going to talk about it again. But in statistics, there is this Conway diagram, which is a Venn diagram that says, well, it is a combination, intersection of these three things is the data science. And you will notice here, for people like me who are computer scientists, there is no role. It's just hacking skills. And in the blog post that he writes on this, he actually says, this does not require a background in computer science. In fact, many of the most impressive hackers I have met have never taken a single CS course. Well, there you go. So when statisticians argue the point, some of the statisticians at least, they basically say it's all hacking, nothing more than that. But statistics is the fundamental part, along with domain expertise. You can imagine that I think both of these are total nonsense. They don't mean anything. In fact, this idea of building Venn diagrams and adding more detail to it seems to become very popular. Believe it or not, there is a website that's entitled Battle of Data Science Venn Diagrams. I have no interest in going into these discussions. For me, if you want to define what is who owns data science, the issue is that we start with the constituents. Who are the constituents of data science? I can name three, maybe you can name more. One is the core technologists, which is in the STEM core, people like me who are involved in doing data engineering solutions or involved in developing machine learning algorithms and so on, or security privacy technologies and so on. So those are one group of constituents. The second group is STEM, but they're application people. So the physicists, biologists, etc. These are people who are involved in data science applications in some domain. They own the problem and they are interested in solving it using a data-driven approach. And the third constituent is non-STEM people in social sciences and humanities. They may own applications. For example, digital humanities is a very interesting application domain, and in that sense, they're similar to the second category, or they might be people focusing on ethics, social impact, policy, and legal issues. And data science, therefore, is much broader than those Venn diagrams suggest. And if you're really going to use a Venn diagram, I still like my Venn diagram a lot more in being inclusive. Now, let me touch upon who's a data scientist. I promise that I will answer this. For me, based on the definition of how I view data science, my view is that a data scientist should have these core competencies. Data scientist should be someone who has in-depth, expert-level knowledge in at least one of the two areas, technical areas, which is data engineering or data analytics. And this is an expert-level knowledge. And she should have passing knowledge and acquaintance with the other two pillars of data science. She should know what the ethical problems are in building data science solutions, and she should know what the privacy and security concerns are. And the third core competency is that the person should have in-depth knowledge. I don't mean expert level, but enough knowledge in at least one, preferably multiple application areas to be able to work with problem owners in those areas. And that leads me to the fourth competency, which is being able to work in a team and being able to communicate. Data science is a team effort, and we work in that community. So that's my answer. Let me skip this. My final thoughts, data is central and it's increasing in volume and complexity. And data is important. And if you treat data well, and if you analyze it correctly, it is going to tell you a story that might be important. It might confirm your hypothesis, or it might refute it, or it might reveal something totally unexpected. But it will tell a story if you treat it right. It is the data science is multidisciplinary, multifaceted, and you need to treat it as such. And to answer the question of whether data science is a discipline, well, it may not be a discipline yet, but it can certainly become one if we take a systematic approach to it. Finally, let me end by just simply saying that my view is very much STEM-centric, and it's really computer science-centric. And there is far more. There is a whole domain of data science and social sciences that I am now studying. I'm not knowledgeable enough to talk about it, but don't get the impression that from my presentation that there isn't that huge domain of data science and social science. There is, but I don't know how to talk about it yet. With that, I end. Thank you very much, and I'm happy to take questions. And let me stop my sharing.
Hocam çok teşekkürler. Çok ilginç bir konuşmaydı. Çok teşekkür ederiz.
Biraz uzun oldu, kusura bakmayın.
Yok, çok ilginçti gerçekten her yönüyle. Tabii daha çalışacağımız çok konu var data science konusunda, sizin de söylediğiniz gibi. Özellikle bu algoritmaların yanlı olması, yanlı olmamasına çalışırken bile sizin söylediğiniz gibi bazı sonuçların yine de yanlı çıkması gibi değişik açılardan tabii ki çalışılmamız gereken çok konu var. Birkaç soru için vaktimiz varsa...
Var.
Tamam. Dinleyicilerimizden gelmiş. Tabii konuşmanızın başında bir kısmı. Şöyle, if you remember any, could you share name of some special interest groups that works on environmental research to help our world to become more sustainable and healthy diye bir dinleyicimiz sormuş.
Ben de İngilizce cevap vereyim. I don't know any special interest groups that focus on that topic. There isn't even a huge number of special interest groups that are focusing on data science in general. They will emerge. We've started to have journals on data science and conferences on data science. So the interest groups are going to come out. I'm trying to form a group both locally and within Canada that works on data science issues in sustainability, but we're at very, very early stages. I cannot tell you that we're a formal group. We're kind of chatting group more than anything.
Teşekkür ederiz. Bir dinleyicimizden daha var. Technology is continuously evolving. What is beyond data science? Diye bir sorusu var. Aslında sorusu devam ediyor ama ona bir kısım cevap verdiniz. İkincisini de okuyayım ama zaten yani bu tabii ki sunum sırasındaydı. Sunum ilerledikçe cevap vardı aslında. Since data science is interdisciplinary, can we say that data science is one of the rare scientific fields that is not belonging to only engineers gibi bir sorusu var.
Yeah, the second part is easy because I think I answered it. It does not belong to engineers. It does not belong to computer scientists. It does not belong to statisticians. It is really broad, and the challenge is that you want to be inclusive. So you bring in these fields, but you don't want to be so inclusive that you cannot define your core. In other words, you're just diffused. You're just anything. And what I try to do, the way that I try to think about this is that I want to define that core, but in an inclusive fashion. So that was my talk But the first part of it, what comes after data science, I really have no idea. I'm horribly bad in making predictions. If I could predict what comes after data science, I might go off and start doing it and become rich, but I have no idea.
Evet hocam. Bir sorumuz daha var. Sunuma ulaşabilir miyiz diye bir dinleyicimiz sormuş.
Tabii ben PDF ya da animated PowerPoint versions göndereyim size.
Tabii o zaman
yapabilirsiniz.
Dinleyicimiz ITI üzerinden bağlantı kurursa ona sunumu eriştirir.
Tabii sizlerle temasa geçerse yapabilir.
Genetik alanındaki uygulamalar için genel olarak hangi veri yapıları kullanılmakta gibi bir sorusu var ama hocam yani o genetik herhalde uygulamaları çalışan
sanırım onlara sormakta çok daha yarar var. Ben tam olarak bilmiyorum onu.
How should we treat time series data when analyze it? Could you please say some methods to start analysis? Can we treat it as discrete, not continuous data? Gibi bir sorun.
Okay. I'm assuming the questioner is making a differentiation between streaming data and time series data, because streaming data also has a time dimension, which is that the data arrives with certain timestamps that tell you when the data was generated or when the data came. So I'm leaving streaming aside. For streaming, there are systems that are being built. My research group is working on streaming data as well. But for the time series data, depends on what you really want to do, and it depends on what processing you're worried about. In my field, which is really data management, there is the temporal database line of research where within the database we store intervals in which data is valid, and you can then query asking for data that was valid in a particular time range. So there are solutions of that type. Beyond the short answer, digging in is really a totally separate talk. So let me stop there. But you need to make a distinction between time series data is in the streaming sense and time series data in non-streaming sense.
Çok teşekkürler. Hocam süremizin de sonuna geldik. Çok teşekkür ediyoruz. Bir soru daha var. Hemen kısaca sorayım mı?
Tabii.
Tamam. Bildiğiniz üzere derin öğrenme birçok alanda ilerleme gösterdi. Ancak modellerin kompleksliği dolayısıyla black box olarak yorumlandığı olabiliyor. Sizin derin öğrenme hakkındaki düşünceleriniz nelerdir gibi bir soru var.
Okay. Ben öncelikle machine learning ve derin öğrenme konusunda bir uzman değilim. Benimki dışarıdan görüntüleme. Dolayısıyla söyleyeceklerimi biraz ona göre değerlendirmenizde yarar var. Derin öğrenme, ben anlatırken bahsettiğim data analytic tiplerini predictive ve prescriptive data analytics tiplerinde derin öğrenmenin rolü var tabii. Genellikle o tip analizlerde kullanılıyor. Belirli uygulamalarda çok iyi sonuç verdiği kesin. Şu benim bildiğim kadarıyla, yanılıyor olabilirim gene benim konum olmadığı için. Sıkıntı hangi uygulama alanlarının hangi karakteristikleri iyi sonuç vermeyi doğuruyor. Yani derin öğrenmeyi hangi uygulama alanlarında da en iyi uygulanabilir? Bunun bir yok, sistematik bir açıklaması yok. Buna uyguluyoruz, iyi sonuç veriyor. Buna uyguluyor. Yani dene bul sistemi şu anda uygulanıyor ve o normal. Yani bu araştırmaların ilk aşamalarında böyle olması doğal. O bir sorun. Daha sistematik bir şey yok, sınıflandırma yok. İkincisi de bunun explainability dediğimiz açıklayabilme sonuçları, yani niye model böyle sonuç veriyor? Onun açıklaması yeteri kadar iyi yapılamıyor şu anda. O konuda çok fazla bildiğim kadarıyla de öğrenme konularında ki arkadaşlar çalışıyor ama ben uzmanı değilim. Yani bu söylediklerimi bir başka uzmanla kontrol etmenizde yarar var.
Çok teşekkürler hocam. Bence çok bilgilendirici oldu. Vaktinizi aldık. Çok teşekkür ediyoruz. Çok ilginç bir konuşma oldu bizler için de. Burada da konuşmamızın sonuna geldik. Sizin eklemek istediğiniz son şeyler varsa onları alabiliriz. Sonra da bugünkü ilk seminerimizi, ilk söyleşimizi sizinle başladık. Çok teşekkür ediyoruz tekrar. Bitirebiliriz.
Ben teşekkür ederim davetiniz için ve bu olanak için. Bekleyeceğim fazlaca bir şey yok. İnşallah bir dahaki seferki semineri canlı yaparız İstanbul'da.
Onu biz de çok istiyoruz hocam. Zaten özledik böyle karşılıklı seminer yapmayı. Sizi de burada görmek, davet etmek, yüz yüze görüşmek çok isteriz. Mutlaka en kısa zamanda olması dileğiyle. Çok teşekkürler. Umarım şöyle. Peki. Evet. Katılımcılarımıza da dinleyicilerimize de çok teşekkür ediyoruz. Seminerlerimiz bundan sonra tekrar devam edecek. Duyurularımızla sizlere ulaşmaya çalışacağız. Çok teşekkür ediyoruz katıldığınız için.
Teşekkürler, iyi günler.
İyi günler.